Good afternoon. This is Gerhard Hüsken from Oberwolfach. Our speaker this session is Zhifei Zhang from Beijing University. He will talk to us on hydrodynamic stability at high Reynolds number and the transition threshold problem. Please.
Okay, thanks, Professor Hüsken, for the introduction. I'm very honored to give a talk at ICM 2022. So let's begin with the Reynolds experiment in 1883. This is the picture of a Reynolds experiment. If you are interested, you can find the videos from YouTube. Yeah, in this experiment, it was found that the state of the flow is determined by a dimensionless constant called Reynolds number, defined by rho Lu of mu. Here, rho is the density, L is the diameter of the pipe, U is the velocity, and mu is the viscosity. It was observed that when the Reynolds number is small, the flow is in the laminar state. And when the Reynolds number exceeds some certain limit, then the flow becomes unstable and then evolves into a turbulence state. So this is a very interesting physical phenomenon. So now the question is, what's the physical mechanism or mathematical principle behind it? As we know, a basic mathematical model describing the motion of the incompressible viscous flow is the Navier-Stokes equation. Here, V is the velocity, P is the pressure, nu is the viscosity coefficient reciprocal to the Reynolds number. So the first equation is the momentum equation. The velocity is divergence free, which means the flow is incompressible. And we impose non-slip boundary condition on the velocity. For the simplicity, the fluid domain omega is usually taken to be a channel domain or a pipe domain. For the channel domain, X is the stringwise direction, could be taken to be periodic or infinite. Z is the spanwise direction, usually periodic. And for the pipe domain, Z is the stringwise direction. And R is the radius of the pipe. Now we give some examples of laminar solution for the Navier-Stokes equations. Plane quiet flow Y00 may be the simplest laminar solution, which describes a laminar flow between two parallel plates in relative motion. Plane Poisson flow 1 minus y squared 00 is another laminar solution widely studied by physical communities, which describes the laminar flow between two fixed parallels. And the pipe Poisson flow is of special interest because it is one of the simplest mathematical idealization of Reynolds experiment. From the mathematical perspective, our task is to study the stability and the instability of laminar flow at a high Reynolds number. A traditional method studying the linear stability is to consider the linearized Navier-Stokes system along the laminar flow. Here, L nu is the linearized operator, and then we consider the eigenvalue problem. Here, capital U is the eigenfunction, and the lambda is the eigenvalue. So if the real part of all eigenvalues is negative, then the system is linearly stable. Otherwise, if they exist eigenvalues with positive real part, then the flow is linearly unstable. Now the eigenvalue analysis showed that the plane quiet flow is stable for any Reynolds number. And the plane Poisson flow is stable for Reynolds number less than 5,772. In a recent work with Wien and with Chen and Wei, we proved that the pipe Poisson flow is linearly stable at a high Reynolds number. A folklore conjecture is that the pipe Poisson flow is stable for any Reynolds number. To completely solve this conjecture, we may need to use a computer assisted proof to deal with the case of median Reynolds number. On the other hand, experiment and numerical simulation indicated that this flow could transit to turbulence when Reynolds number exceeds a certain critical number. For example, for a plane Poisson flow, the transition happens at a Reynolds number 350. And for a plane Poisson flow, the transition happens at a Reynolds number 1000. So this transition number is much smaller than the critical number predicted by eigenvalue analysis. So this kind of transition is called subcritical transition. In some literatures, this inconsistency between eigenvalue analysis and experiment is so-called Sommerfeld paradox. Understanding this transition mechanism is of great interest in fluid mechanics. To shed some light on the transition mechanism, Trefethen et al. Proposed the transition threshold problem, which asked how much disturbance will lead to the instability of the flow and the dependence of disturbance on Reynolds number. Below is the mathematical formulation of this problem, formulated by Berjosian, Chapman, and Mahmoudi, which is stated as follows: given a known, find a beta which may depend on x, such that if the x known of the perturbation is much smaller than RE minus beta, then the flow is stable. If the perturbation is much bigger than RE minus beta, then the flow is unstable. This critical exponent beta is called the transition threshold. Afterwards, there are a lot of works to compute the transition threshold for different laminar flow, like the Couette flow and Poisson flow, via experiment, numerical, and asymptotic analysis. So let me just mention two results. One result is numerical result by Landbrad et al. And another one is asymptotic analysis result by Chapman. From this table, we find the results in two ways are not consistent in some cases. For example, for the Couette flow and oblique perturbation, beta equals 5/4 by numerical analysis, and beta equal to 1 by asymptotic analysis. And for the Poisson flow, numerical results and asymptotic analysis results are different for two kinds of perturbations. In fact, the community does not reach a consensus on the transition threshold. So this gives us another motivation to study this problem in a rigorous mathematical way. So we review some rigorous mathematical rigorous analysis result. First of all, we consider the Couette flow in this domain. Here with the infinite y direction, this choice of the domain avoids the difficulty caused by bound layer effect. And Berjosian, Chapman, and Mahmoudi proved that if X is a Zhifei class, then beta is less than 1. If X is a Sobolev space with high regularity, then beta is less than 3/2. In this joint work with Wei, we showed that if X is a Sobolev space H2, then beta is also less than 1. So this result means that above H2 regularity, the transition threshold is irrelevant of the regularity of the perturbation. And more importantly, these results confirms Chapman's asymptotic analysis result. So by the asymptotic analysis, beta equal to 1 for both perturbations. Okay. In a recent work with Chen and Wei, we proved that the transition threshold is still less than one, even with the boundary effect. I'm going to talk about this result in detail. In this work with Li and Wei for the Kolmogorov flow, we proved that the transition threshold is less than 7/4, but we believe this result should not be optimal. From this work, we find that the following factors play a crucial role in determining the transition threshold. 3D lift up, this may be the worst instability effect, which will lead to a transient growth of the solution. Bound layer effect, this is due to the existence of warm modes near the boundary and also central modes near the critical points of non-monotone flows like the Perturbation flow. The inviscid damping and enhanced dissipation are two kinds of good effects. Both phenomena are due to the vorticity mixing induced by shear flow. I will introduce them in a minute. Like a nonlinear wave equation, now structures of nonlinear terms will also have a crucial effect on nonlinear stability. So the main difficulty of this problem is to reveal how these bad effects and good effects influence nonlinear stability via complex nonlinear interactions. So before introducing the transition threshold problem, we first give a brief introduction to linear inviscid damping. We consider the linearized 2D Euler equation along the shear flow in a finite channel. Here, omega is the vorticity, L is the linearized operator defined as follows. In particular, for the Couette flow, the linearized equation is reduced to a transport equation of the vorticity. So any LP node of the vorticity is conserved. Yet in 1907, all found that the velocity could decay to zero. Also, the vorticity is conserved. So this phenomenon is so-called the inviscid damping, which is similar to the Landau damping in plasma physics. In this joint work with Wei and Zhao, we proved the linear inviscid damping for a class of monotone shear flow with under a spectral assumption. The linearized operator L has no embedding eigenvalues. More precisely, if the average of omega 0 equal to 0 and the PD omega 0 equal to 0, where PD is the spectral projection to discrete spectrum, then the L2 node of the velocity decays T-1. If the initial vorticity has more regularity in y direction, then the second component of the velocity decays T-2. Moreover, these decay rates of the velocity are optimal. So the spectral assumption holds automatically when the flow has no inflection points. And in this work, we proved the linear inviscid damping for a class of symmetric flow with a non-degenerate critical point. An important example is the Perturbation flow, y square. In fact, for general non-monotone shear flows, we can also prove the linear inviscid damping. In a sense, L2 space-time estimates, not in the pointwise. Here is the estimate is in a pointwise of time, but here is in the L2 space-time estimate is uniformly bounded for any alpha. We have the same result for the Kolmogorov flow in a rectangle periodic domain. Here, delta less than 1 is to ensure the flow is linearly stable. So in this case, the spectral assumption also holds automatically. I would like to give a remark for non-monotone shear flows, except the vorticity mixing, a new dynamic phenomenon called vorticity depression has a crucial effect. The vorticity mixing means that the vorticity at a critical point will decay to 0 as t tends to infinity. So this phenomenon was first observed by Boucher and Morita. And in this work, we confirmed this phenomenon for general non-monotone shear flows. The key ingredient of the proof is to solve the inhomogeneous Rayleigh equations, which is second order ODE equations. The main difficulty is when C is close to the range of U, the coefficient U minus C is degenerate. So for monotone shear flow, we can use a direct method to construct two linearly independent solutions for homogeneous Rayleigh equations. So this method also works well for the symmetrical shear flows, because in this case, we can make an even and odd decomposition for the solution. But this method, but for the general non-monotone shear flow, the direct method is hard to use. For this reason, we've developed a compactness method, which does not rely on the representation formula of the solution. And based on contradiction compactness argument and blow-up analysis near the critical points of the flow, we can prove the H1 known of phi is uniformly bounded by H1 known of F. From these estimates, we can deduce the L2 space-time estimates of the velocity by taking the Laplace transform for the linearized Euler systems. Motivated by the wave equation, we also develop a vector field method to give a new proof of linear inverse damping for monotone shear flows. For this method, the main trouble is the vector field. The vector field X, capital X, just commutes with the transport operator, not linearized operator with non-local part. So our observation is that the non-local part could be viewed as a perturbation once we have the space-time L2 space-time estimates of the velocity, which can be obtained by the compactness method. Okay. Let's also mention some important progress on nonlinear inverse damping. This topic is, I think, is much more difficult. Many interesting problems remain open. When the perturbation is in a Zhifei class 2, the nonlinear inverse damping for the Couette flow has been proved by Josing and Mahmoudi. And for stable monotone shear flow, independently proved by Reynolds and Mahmoudi Zhang. Unlike linear inverse damping, nonlinear inverse damping much depends on the regularity of the perturbation. When the perturbation is in a Sobolev space with low regularity, they exist the steady non-shear solution near the Couette flow, proved by Lin and Zheng. And for the perturbation in a Zhifei class 2 plus, the nonlinear instability for the Couette flow has been proved in some sense by Deng and Mahmoudi. Now we give a brief introduction to linear enhanced dissipation. So we first look at the linearized 2D Navier-Stokes equation along the quite flow. So when X is periodic and Y is infinite, then the solution have the following explicit formula in the Fourier variable. Due to this inequality, if the average of omega 0 equal to 0, then the L2 norm of the vorticity is bound, it decays exponentially as rate nu 1/3. So this decay rate is much bigger than the diffusion rate nu. So this phenomenon is so-called enhanced dissipation. Similar phenomena could be observed for general shear flows like the Kolmogorov flow. So the below is the linearized Navier-Stokes equation along the Kolmogorov flow. Compared with the Couette flow, this flow is non-monotone, and the linearized operator has a non-local part. So it turns out this will lead to many essential difficulties in the proof. Based on numerical analysis for the spectrum of linearized operator, Beck and Wiener conjectured that the L2 norm of the vorticity decays exponentially nu 1/2. So here the decay rate is smaller than that for the Couette flow. This because the Kolmogorov flow has a critical point. Is not a monotone flow. Okay. So now we have developed 3 approaches solving Beck and Wiener's conjecture. One is the wave operator method. As we mentioned above, one of the main difficulties comes from the non-local term. So motivated by the scattering theory in quantum mechanics, we can construct an operator D called a wave operator to eliminate non-local parts. Moreover, the operator D we constructed enjoys some properties like the unitary operator. Then the new quantity, new unknown, d omega, satisfy an equation without non-local term. 2 is resolvent estimate method. The key ingredient of this method is to establish the resolvent estimate for the linearized operator. Here, L nu is the linearized operator after taking the Fourier transform in X, and the beta bigger than 1 is the wave number in the X. So from these resolvent estimates, we can deduce the enhanced dissipation estimate by using Gerhardt plus type lemma for a creative operator proved by Wei. 3 method is the hypercoercivity method. So here we consider the linearized Navier-Stokes equation along the Kolmogorov after taking the Fourier transform in X. So the key idea of this method is to construct a suitable energy functional, which is positive and decreasing in time at least. So this method works well for the linearized operator without non-local part, but is not directly available for the linearized operator with non-local part. Due to the special structure of the Kolmogorov flow, here we can construct a modified energy functional. Compared with the usual energy functional, there are 2 main differences. The first point is to use a new inner product. And the induced norm to define the energy. And the new inner product, the operator B and C are symmetric, and the induced norm is equivalent to the usual L2 norm when beta is bigger than 1. Another new point is to introduce a suitable time weight in front of the energy, which are crucial to obtain a sharper estimates. Let me mention an independent different proof by Ibrahim Maekawa and Masmoudi. let's give a few comments about the three methods. The first method is robust, but the construction of the wave operator is quite complicated. The last two methods, especially hypercoercivity method, much rely on the structure of the flow. Recently, we developed a compactness and resolvent mixed method for which might be applicable for general shear flows. Now let's come back to the transition threshold problem. And analyzing the original Navier-Stokes system is quite complicated. So we first look at a toy model introduced by Chapman, which is a coupled system of string-wise modes and oblique modes. In physics, Psi1, phi1 could be filled as string-wise vorticity and string-wise streak, respectively. And Psi2, phi2 could be filled as oblique modes. Here, epsilon is much smaller delta. This because the enhanced dissipation of the oblique modes. For example, delta equals epsilon 1/3 for the Couette flow. Due to the lift upturn Psi1, phi1 will undergo a transient growth in a time during a time period of 1 of epsilon. And also the selection of nonlinear terms takes in account nonlinear interaction in the real systems. For example, nonlinear terms phi1 times phi2 corresponds to the worst interaction between streak and oblique modes in the Navier-Stokes systems. Here we just observe the dynamics of this toy system in a time scale 1 of epsilon, because the solution will undergo transient growth in this time scale. So we make this scaling for the time. Now we analyze the scale of the unknowns. From the second equation, Psi1 has the same scale as epsilon phi1, and from the fourth equation, Psi2 has the same scale as delta phi2. On the other hand, in order for nonlinear terms take to effect, linear term and nonlinear term should balance, taking all into considerations. So the unknowns should have the following scale. So the below is the rescaled toy system. And for chirality, we rewrite the system of oblique modes as follows. So Psi2, phi2 is the rescaled oblique modes. From this the system, it's easy to see that if phi1 is bigger than 1, the system has unstable eigenvalues. This is so-called the secondary instability of oblique modes. Otherwise, the system is stable, and the oblique modes will rapidly decay to 0 because the coefficient delta of epsilon is very large. Okay, so this scaling analysis indicates that the transition amplitude of this toroidal model should be epsilon delta squared. So this picture shows one root of the transition root. The energy is first transferred from the string-wise vorticity to the string-wise streak. Due to the lift up, the energy has a magnification of 1 of epsilon. Now there are two situations. If the energy of string-wise streak is much bigger than delta square, then the oblique system is unstable. Otherwise, the system is stable. The transfer of the energy forms a sustainable loop. So in summary, for this toy system, two instability mechanisms are similar to the Navier-Stokes similar to the Navier-Stokes system. One is the mechanism of the energy transfer from the string-wise vorticity to the string-wise streak via a lift up. Another is the secondary instability mechanism of oblique modes. Now we get back to the Navier-Stokes systems. We first introduce the perturbation system along the Couette flow. Here U is the perturbation of the velocity, omega is the perturbation of the vorticity. Following the physical literatures, we would like to use the coupled system in terms of Laplacian U2 and omega 2. This formulation plays a crucial role in our work, both in our work and Bergiosi, Masmudi, and Yuman and Masmudi's work. So the main advantages of this formulation is that this is no pressure turn in this system, and the Laplacian 2 enjoys a good structure like the vorticity in 2D flow, and omega 2 has a vanishing boundary conditions, and also for the Laplacian U2, the boundary condition could be viewed as a non-slip boundary conditions, and the equation of omega 2 contains a lift up term partial C U2. That's what I mean 3D lift up, which is absent in 2D. We prefer to use the system after the Fourier transform in X and Z. Here alpha is the wave number in X and beta is the wave number in the Z. So when K is not equal to 0, the nonlinear term, all the other components of the velocity and vorticity can be recovered from U2 and omega 2. And also the nonlinear term behaves as follows. So here each term only depends U2 and omega 2. And for F1 alpha beta, the middle part is the worst. Nonlinear interaction because omega 2 has a lift up effect, and second order derivative in y direction falls on the unknowns. So we look at now we look at the secondary instability mechanism for the Navier-Stokes systems. So for this purpose, we consider the linearized Navier-Stokes system and seek the solution of this form. Then we and Ada solves the following eigenvalue systems. Here I equals nu minus 1. So here we would like to know how large the perturbation. As we know, the Couette flow is linearly stable for any Reynolds number. So all eigenvalues of this system are stable. So we would like to know how large the perturbation induced by nonlinear interactions could excite unstable eigenvalues. Following Chapman's asymptotic analysis, we consider a class of eigenvalues with imaginary part of order alpha r minus 1/3. So this class is called Wall modes, whose eigenfunctions are localized in a region of order alpha r minus 1/3 near the boundary. To excite unstable eigenvalues, we introduce a perturbation f into the eigenvalue equation of V. So we first check the left hand side, the scale in the inner layer. So lambda minus y is of order alpha r minus 1/3. Because the thickness of the inner layer is alpha r minus 1/3, and V vanishes on the boundary. So the partial y square V is of order alpha r 2/3. So in conclusion, the left hand side is of order alpha r 1/3. Now we check the scale of the perturbation f. As we know, the worst interaction of is set between streak and oblique modes. So like the eta bar is the string-wise string-wise mode and times VYY. So here as our wall mode, VYY is of order alpha R two-thirds. So to excite unstable eigenvalues, the both sides should have the same scale. So Li bar should be of order alpha R minus one-third in the inner layer. So this requires that Li bar is of order O1 in the outer layer, because partial Y Li bar has the same scale as Li bar, and Li bar vanishes on the boundary. On the other hand, due to the lift up effect, Li bar has the same order as RV bar. So this requires V bar is of order R minus one. So this scaling analysis suggests that the transition threshold beta equal to 1 for the Couette flow. In this joint work with Chen and we confirmed this scaling analysis result. So our result is stated as follows: if the perturbation, if the H2 node of the perturbation is much smaller than nu, then the Couette flow is nonlinearly stable, and we have the following uniform bounds for the solution. And compared with the initial perturbation, the energy of string-wise mode U1 has a growth nu minus 1 due to the lift up effect, and the string-wise mode U2 and U3 are uniformly bounded by the H2 node of the initial perturbation. And like the linearized system, the oblique mode has an enhanced dissipation estimate. Here's nu one-third. And also the bound of oblique mode U2 is better than set of source of U1 and U3. This because Laplacian U2 enjoys a good structure like the vorticity in 2D. Now we outline the three key ingredients of the proof. So the first key ingredient is to establish the space-time estimates. Space-time estimates for the linearized system. To control Laplacian U2, we needed to consider the linearized Navier-Stokes system with Navier-slip boundary condition, and to control omega 2 is Navier-slip boundary condition. Laplacian U2, we needed to consider linearized system with non-slip boundary condition. For example, for the linearized system with non-slip boundary condition, we can prove the following space-time estimates of the solution, which incorporate all linear effects I mentioned earlier. For example, this exponential decay is due to the enhanced dissipation, and the L2 space-time estimate of the velocity is due to the inviscid damping. And here the loss nu 1/2 in front of this quantity is due to the bound layer effect. The proof is based on the resolvent estimates method developed in this work. The second key ingredient is to exclude secondary instability. This step is the most difficult in the proof. For this purpose, we needed to prove the linear stability for the flow V, which is a small perturbation of the Couette flow in the sense the V is close to Y in the H4 node, and V minus Y is vanishes. Here, A nu V is the linearized operator, along this flow. So our task is to exclude the existence of unstable eigenvalues of linearized operator. Instead of consider the coupled system of Laplacian U2 and omega 2, the key idea is to introduce a coupled system of W, capital W and capital U. Then the linear stability can be reduced to solving the following Sommerfeld system based on the resolvent estimate the method and many delicate tricks like the introduction of the good unknown and and the construction of the boundary layer correct, we can prove the following uniform estimates, especially when the force equal to 0, the solution, the OS system has only trivial solution. So that implies the linear stability of the flow V. And the third, to prove the nonlinear stability, the third ingredient is to construct a suitable energy functional, which consists of three parts. The first part is to control the string-wise modes. Here, a crucial decomposition of this decomposition is crucial. The first part corresponds to the interaction between string-wise mode, and the second part corresponds to the interaction between oblique modes. The main reason making this decomposition is to avoid estimating higher order derivatives of oblique modes. So the energy E1 is to control the string-wise mode U1. For U1 0, we need to control H4 node, which is necessary to exclude the secondary instability. And for the U1 not equal, H2 node is enough. E2 is to control the string-wise mode E2, U2, and U3. So the first two parts are natural, and the last three parts consider the boundary layer effect by introducing a suitable weight. So the estimates of E1 and E2 are based on the direct estimates for the system of the string-wise modes. The second part is to control the oblique modes in a semi-linear way. What I mean is that this estimate is just based on the space-time estimates for the linearized Navier-Stokes systems. So the definition of E3 is consistent with the space-time estimates we have derived for the linearized Navier-Stokes systems. And the E4 is to control the oblique modes U2 and U3 in a quasi-linear way. What I mean is that the estimates E4 is based on the space-time estimates for the coupled system U, coupled system U, and the coupled system U and W. So this part is crucial to control nonlinear interaction with lift-up effect, such as the interaction between string-wise mode and oblique mode. For example, we can control listen in this way. Here, U1 is bounded by nu t. So listen to absorb the listen, we need to increase the exponential power. So okay. So in conclusion, combining the space-time estimates with the nonlinear estimates, we can conclude a closed energy estimates where the energy E1 is of order 1 due to the lift-up effect, and the other energy is of order nu. It's order nu. So in spite of this progress, I think that this topic is just the beginning. There are many interesting problems to be studied. For example, the transition threshold problem for the plane Couette flow in infinite channel. So because in this case, the lift-up effect should be weaker than the case of finite channel. So the beta may be strictly less than 1. And for the plane Poisson flow, based on the asymptotic analysis result, the transition threshold beta should be equal to 3.5. I think the most interesting problem is the transition threshold conjecture for the Poisson flow. For this flow experiment, the numeric and the asymptotic analysis all conclude beta equal to 1. And finally, the question, I think for the problem is quite interesting if the other physical effects are introduced into the system. I will stop it here. Thanks a lot for your attention.
Thank you very much for your lecture. Unfortunately, we cannot have live questions, so please direct any questions directly to the speaker by email or use the discourse forum set up on the website of the ICM. Thank you everyone for attending. Bye-bye.
Bye-bye. Thank you.
Thank you very much. Great lecture.
Thank you, Professor. Okay. Bye-bye.
Bye-bye. I'm not sure the assistant is coming back on.
I am here.